Okay, our next speaker is Zoe Barbeau from Stanford University. She's studying engineering. Her advisor is Sanjeeva Lele, and she's done 2 practicums at Lawrence Berkeley National Laboratory. Zoe, let's welcome Zoe.
Hi, today I'm going to talk about numerical methods for multi-phase compressible flows, as well as acceleration of vortex methods. I'd also first like to acknowledge support from the DOE Predictive Science Alliance project. So what am I interested in? I'm interested in simulating a 3D planar 2-phase mixing layer. What this consists of is a high-speed gas stream flowing next to a liquid stream. And this is prototypical of a process called atomization, where this liquid stream becomes unstable, has ligaments that stretch out and eventually break up into droplets. It has a lot of different applications in different spray processes, as well as combustion. We're particularly interested in the mixing stage preceding combustion in rockets. But one of the main challenges with these sorts of simulations is for multi-phase simulations, you have a wide range of scales. Because you have from the length scale of this liquid stream of the jet down to very, very small droplets. And it's important to resolve all these scales well to have an understanding of the breakup process of the jet, which then can be used to improve these atomization processes. And this requires use of large-scale HPC. But before we can get to that step, we need a numerical method that addresses the challenges of compressible multi-phase flow. And we're particularly interested in high-order methods. So first, let's talk about the governing equations. Mainly what I want to get across is there's 2 main ways to look at multi-phase simulations. And one is a sharp interface method, and that would be where you have a sharp interface between the gas and the liquid. And usually you explicitly track the interface in these methods. The other way is to have a diffuse interface. And so instead of it being a sharp jump, the interface is diffused over several grid points between the liquid and the gas. And this is the method that I'll be using. The governing equations for this kind of method consist of, or one variant is to have a volume fraction equation, where it has the volume fraction of the gas and the liquid, mass, momentum, and energy equations. But what I really want to get across is these additional terms highlighted in red and blue. The ones here in red are interface sharpening terms. One of the main issues with diffuse interface methods compared to sharp interface is your interface will diffuse over time numerically, and it's not physical to have a liquid mixing with a gas. But if you have these interface sharpening terms, they numerically sharpen the interface so that you maintain separation between the 2 phases. Then I also have localized artificial diffusivity terms, both in the material equations and then also for shock capturing purposes. So let's now talk about the challenges of multi-phase methods. We have high density ratios. We need to represent the interface. We need to maintain positivity of the 2 species and also resolve a wide range of scales. How I'm addressing that is by using a 6-ordered staggered compact finite difference scheme and treating the interface with material LID and interface sharpening. So what is the compact finite difference scheme? Here are the stencils for the interpolation and derivative that I'm using. And here is a plot of the modified wave number for my 6-order staggered scheme and a 2nd-order central scheme. And what I want to get at here is the reason we want to use this higher-order method is that for a given range of wave numbers, the lower order scheme accurately represents a smaller range of wave numbers, whereas the high order method accurately represents a wider range of wave numbers. And this corresponds to our desire to resolve a wider range of scales. Now, additionally, the 6-order staggered, the way it works is I do interpolation step on my primitive variables, and then I construct the fluxes to evolve my quantities and take the derivative at back to the node points. The node points are here, and then I have the staggered points are at the 1/2 phase. And the reason we do this is because it provides greater robustness One common issue with high order methods is aliasing error, where you have high order content that causes numerical oscillations. A common method to remove high order content from compact finite difference schemes is to apply a filter that just removes it. However, with the staggered method, the interpolation acts as a low pass filter and improves decreases the amount of aliasing error you have. And this significantly reduces the need for filtering, which has been shown previously for compressible single phase flows. Now, I'll talk about positivity. We have this material LAD in the mass and volume fraction equations, where it has sensors that detect two things. First off, we have high order derivatives of the volume fraction and mass fraction. And this acts to detect any sort of numerical oscillations. And then we have these terms here, which act to detect any sort of out of bounds value in the mass and volume fraction. And these terms greatly limit the out of bounds values present in the code. This here is an example of a shock moving through a liquid and hitting a gas bubble. This case is a test of robustness for the method. The positive values can cause the simulation, or negative values can cause the simulation to fail. But with the material LAD, we're able to run this test case robustly. Now I'm going to talk a little bit about linear stability theory. So again, what I'm interested in is a two-phase shear layer where we have the liquid stream and the gas stream. And one way we can verify our method as well as explore the physics is to look at linear stability theory. What it is I linearize the governing equations in terms of a perturbation where we get the temporal growth rate of the shear layer for different wave numbers. So with this, we're able to see if the method accurately captures the early stage evolution of the shear layer, so its physical properties, as well as we're able to investigate different effects of density and compressibility on our shear layer. So what I looked at is how does the density ratio of the two-phase shear layer, so the density between the liquid and the gas, affect the overall growth rate, and how does compressibility of the gas stream affect the growth rate of the shear layer? I'm looking at Mach 0.4, 0.6, and 0.8. The dotted lines are the different Mach numbers, where red is 0.8, and then black is incompressible. First off, the cross marks are my corresponding simulations, where I'm able to match between 1% and 4% the linear theory, depending on the level of refinement. The interesting physics that we found is for the low density ratio, you can see a really big jump in the maximum growth rate, depending on if it's Mach 0.8 versus 0.4. And this has been seen in single phase literature, where as you have more compressibility, the growth rate of the shear layer is significantly suppressed. However, as you increase the density ratio between the gas and the liquid, this suppressive effect is greatly reduced, whereas for a density ratio of 1,000, the growth rate is essentially the same for the different Mach numbers. So this is some interesting physics that we're able to learn from the linear stability. So my conclusions is we've developed a numerical method with LAD and interface sharpening to robustly simulate these multi-phase methods. And we've seen some interesting physics in terms of the effective density ratio and compressibility on the two-phase shear layer. And the next steps are to do the 3D study of the shear layer, where now I'll run the large-scale simulations and investigate these effects in 3D. So now I'm going to move on to the work I did at my two practicums. I did my practicums at Lawrence Berkeley National Labs under Phil, and at the second practicum we had collaborators at Oak Ridge, Haight and Sam. This project is on vortex methods. Vortices are very common in nature. They come off plane wingtips. When dolphins blow bubbles, that's also vortex string. So there's a lot of applications. But we really want to look at the HPC side of this. So we're interested in 3D vortex calculations, where we'll be solving this equation. And we're interested in solving it with particles. So we have particles carrying the vorticity. We're using a particle mesh method, which I'll call P3M. And this is to address the challenge of vortex calculations They're quite expensive because you have very many particles. The vortex method we're using, MLC, it represents the far field with where you can solve it with the FFTX or FFT-based calculation. We're using FFTX, which is a FFT library based on Spiral, which is a build-time. It produces targeted high-performance kernels. And then for the particles, we're using Cabana, which is a particle library from Oak Ridge National Laboratory. And we're interested in doing an implementation on the GPU. So how does MLC work? Say this is my grid with a bunch of particles. We have what's called collection particles, which has a correction radius. And then we have a stencil. So this is the grid stencil we're doing our operations on, where we're looking at the particles in this collection. And then finally, we're looking at a specific ith bin. So we do all these operations for an ith particle, an ith bin, and repeat that across the grid. And the calculations are split into having this far field calculation and then accounting for local interactions between the particles. So here is how we're using Cabana. The particles are represented through Cabana, where we carry the position, the velocity, and the vorticity. We represent the velocity on the grid using Cabana grid data. And then really what powers this method is Cabana's list functionality. Cabana can sort particles into lists based on the correction radius, so we know what bins of particles to look at. And we use linked list cell stencil so we can specify the correction radius we're going to look at for these local operations. The steps to the algorithm is first, we just posit the vorticity on the grid to calculate a local velocity. And from that, we take the Laplacian of the velocity and accumulate that. From that, we do the free space convolution, which gives us the velocity on the grid. Then we do a correction step where within that collection of particles, that smaller correction radius, we correct the local grid velocity. And that gives us the far field contribution. Once we have the far field contribution, we interpolate this velocity back to the particles. And finally, we do a local interaction step where we account for particle-particle interactions. In Cabana, there is directly a neighbor parallel 4 that can do these local n-body calculations. But for situations like the deposition and local correction step, where we have this interaction between the grid and the particle, I wrote my own for loops based on the linked list cell stencil to enable this. So first, a little bit of verification. This is the Hills vortex where we know an analytical solution. And we expect a certain convergence, order h3 halves for the particle velocity error. And both on the GPU and the CPU, we get the same answer, and we see the expected rate of convergence. So we verify that our method works correctly. And then here I have some initial results for the different kernels as far as the speed up on GPU compared to CPU, where we see, depending on the problem size, between 10 to 100, kind of averaging around 50x speed up. And then this here is showing as you increase the number of particles per cell, you get a drop in the velocity error, but that's also an area where we'll do some further investigation of the accuracy based on the correction radius, the number of particles, and the grid size. So yeah, next steps are to look at performance, look at a vortex ring, and then what we really want to do is some adaptive remapping of the vortex method. But thank you. I would really like to thank the DOE CSGF and all the members of Krell for all these wonderful opportunities. I've really appreciated being able to do the practicums and do something quite different from my thesis work and learn a lot about HPC.